Example 8 is very similar. But if you've noticed all of the things so far that we've done, we've modified power series, Peter, that have been centered where? Around 0. Good, around 0. And generally, if we switch centers, it's not real easy to modify our series. But in this case, we can, if we want to center something at 1, so long as we can write our function in terms of the same thing, okay? So in this case, like 1 over x, we can't center it at 0 because function's undefined there. And remember, the series and the function it represents always have the same value at the center. So the next most convenient value is 1. So this one wouldn't be too bad to kind of reinvent the machinery using Taylor's rule. But if I can somehow write 1 over x as 1 over 1 minus something, where that something is an x minus 1, then I can shift over my graph 1 unit to the right. So the question is, how can I do that? If I want this to be x minus 1, I need it to be equivalent to x. Well, let's see. We can modify this. If this is kind of what we want, if I really distributed the x, I would have a 1 minus x plus 1, and that would end up with a 1 over 2 minus x. So what I would need to do to get rid of both of those is I would need to what? I need this to be equivalent to 1 over x. Yeah, I would need to add an x and add a 2. Maybe that's not the best way to go about doing it. Let's start with 1 over x. Let's go ahead and first of all do this. What if I did 1 minus x? In order to make that equivalent to x, what would I do? Let's back up even further. How about this? What about x minus 1 plus 1? Are you all okay with that? Okay, so if I do that, now I can group some things together. I can put this one that's at the back and the front, and I have plus x minus 1. Is that the same? And what I'm trying to do is write it as 1 over 1 minus something with x minus 1. So I'm almost there. If I then write this as minus bracket negative parentheses x minus 1, kind of the same trick we did previously, I now have 1 over 1 minus, and on the inside I have negative x minus 1. But because I do have x minus 1, I shifted my graph over 1 unit. So that is equivalent to 1 over x. So I added by adding a clever form of 1, rearranged, and now I can use my rule. So let's go ahead and write 1 over 1 minus x. We get 1 plus x squared plus x cubed. Those are your first 4 non-zero terms plus the nth term plus da-da-da. So if I'm going to create this, really now all I have to do is replace all my x's with what? Negative x minus 1. So I can go ahead and call that 1 over x and replace all of my x's with negative x minus 1. So it's a 1 and then minus x minus 1. And then when I plug it in and square it, I get a positive x minus 1 squared. A negative cubed is going to be a negative, so it's x minus 1 cubed. And then plus dot, dot, dot. Plus, and if I do the same thing here, I'll separate the negative 1 to the n. And then I have my x minus 1 to the n plus dot, dot, dot. So there's your first 4 non-zero terms and your general term. Go ahead and work on finding, if you can, the radius of convergence, if you had to do it on your own. Right. Or have to, yeah. Or not play in the rain, a little bit, a drizzle. As long as it's not light. Right. Okay. Yeah, I did that. Kelly. Yeah, we have to stay off the track. because they're practicing.
And that's for practices. We did practices. That's for
The practices for last Tuesday and Wednesday, and they were gone, so it didn't matter.
And
We have
also for
Thursday. Uh-huh. Yeah.
Because she's asked, she's like, did you set up all those?
Yes.
I was going to start the email. I was like, oh, I was checking to make sure. Yeah, because you had told me.
Yeah, I have the emails from Kelly. Yeah, that was one thing that I was taking care of.
Yeah. Okay. Perfect.
So, I guess I could have left her in the loop, but yeah.
Well, I mean, no.
Yeah,
she
yeah.
told me.
It's all taken care of.
Yeah, because she told me she was like, make sure that you get with Kelly and make those arrangements.
Yeah.
That I had talked to you. Like, you did
Yeah,
that.
it's the only thing is we just need to make sure they stay off the track today. That was Kelly's big thing.
The big thing.
But that's fine. We can respect that. Yeah, we can totally respect that. Yeah. Okay. Yeah. All right. Did y'all figure it out? Ha-ha. So here we go. If this, remember, is what we're calling R, then for the series to converge, that, which is really this, right, because the negative 1 doesn't really matter, has to be less than 1. So we kind of have it, right? If this is the form we want, it's x minus 1, that's x minus our center, has to be less than 1, then our radius of convergence is what? 1 unit. Yeah. And this time, what would be the interval of convergence, or the domain of the power series? If we can go 1 unit left and right of our center, what's our center? 1, right? So 1 minus 1 is 0, and 1 minus 1 is 2. And because it's geometric, can we include the endpoints? No. For the geometric, we're not going to be able to include the endpoints. So there's a quick way, and that's kind of why it's nice to recognize it again as a geometric series. You can get the radius of convergence and the interval of convergence very, very quickly. Again, if you want to draw this little picture, here's your center. Your center is at 1. You're going plus 1 to the left, minus 1 to the left, plus 1 to the right. Okay, let's look at 19 is, as it says, a bit of a moco, a bit of a booger, which means it's fun. Find a power series for h of x centered at 1, and then find the interval and radius of convergence, the first 4 non-zero terms and the general term. Okay, so we're going to have to write that. It's a quotient, right? Something over the quotient of x, so we can possibly write it as some transformed geometric. But we have to be able to write it as 1 over 1 minus something, and then we can also have a number out front. So that's what our goal is. But this has to be 1 over 1 minus. So what can we do first? Let's start with 15 over 2x minus 1. Can I factor the 15 out? Yeah, that's not a bad idea. And now, what can we do? Well, let's do this first. Let's make our center. I'm going to go ahead and do x minus 1, because that's what we eventually need. So if I replace x with x minus 1, it's kind of like completing the square. What did I really just add? I added a negative 2, right? I forced my center to be x minus 1, but by doing that, I really added a negative 2. So to make sure that I'm adding 0, what's the opposite of negative 2? Positive 2. So I forced my center, x minus the center, and then corrected it. So that should still be equivalent. So now I got the 15 out front, and I got the 2 times x minus 1, and then 2 minus 1 is plus 1. So at least I have that. Now I'll flip it around. I got 1 over 1, and now I have plus 2 times x minus 1. And we're almost there, aren't we? All I really need then is to do what we did on the very first one. I need to say it's 1 minus, and then negative 2 quantity x minus 1. And now I've got 1 over 1 minus. And that should be equivalent to what we started with, 15 over 2x minus 1, and it is centered at 1 because it's x minus 1. So let's go ahead and build that one. 1 over 1 minus x, again, is 1 plus x squared plus x cubed plus plus x to the n plus Good. The 15 on the outside, that's probably the last thing you want to do. That's the easiest thing. Distribute a 15 to every term. Your first step should be to go through and replace every x with what? Negative 2 times x minus 1. So I'm going to go ahead and call this 1 over 1 minus. We've got to show it in steps, and it has to be equal on both sides. So if I am not putting the final thing here, I'll do that. So I get a 1. It's going to be minus 2x minus 1. And then when I square the negative 2, I get positive 4x minus 1 squared. Negative 2 cubed is minus 8, and then x minus 1 cubed. So there's the first 4 non-zero terms. And then plus dot, dot, dot. Here's the nice part about it again. You have negative 2 to the n, so you can call that negative 1 to the n times 2 to the n. Again, it's good in the general term if you could separate your alternator from the non-alternator. And then you'll have the quantity x minus 1 to the nth power plus dot, dot, dot. I'm not done. I didn't do that yet, which is why I didn't write it on the left side. Now that I have the hard part done, that's going to require kind of the most diligence right there. Now I will go ahead and multiply everything through by 15. So let me bring that over here where I have some room. All right, so now, Peter, I'm going to multiply by 15 on both sides, and I'll go ahead and call this side now 15 over 2x minus 1. And everything gets multiplied by 15. We have to distribute it to each term. So I'll get 15 minus 30 times x minus 1 plus 60 times x minus 1 squared minus 120 times x minus 1 cubed plus dot, dot, dot. Now here it's going to be a little bit kind of ugly looking. Negative 1 to the n, 2 to the n times 15. There's really no pretty way to do that. Times x minus 1 to the n plus dot, dot, dot. But notice that is counting as the general term, which is one of the true benefits from modifying your existing geometric series, because you might be able to generate the first 4 non-zero terms. You can't use long division because it's not centered at 0, but you could use Taylor's rule. But it's going to be harder to come up with the nth term. So if that's the only way you know how to generate a series, go ahead and do it that way. It's better to get the first 4 non-zero terms and not get the general term than to get nothing at all, okay? Now let's figure out the radius of convergence. For the radius of convergence, remember we take our ratio, which is that right there, that's what we're calling r, and the absolute value of that, which is the absolute value of negative 2x minus 1, which is really the absolute value of 2 times x minus 1, which is really just 2 times the absolute value of x minus 1, right? That has to be less than 1, according to the geometric series test. And because I'm trying to get it as x minus 1 less than the radius, all I have to do is multiply both sides by 1/2, and you get less than 1/2. So your radius of convergence is 1/2. And what is your interval of convergence, or the domain of the power series? 1/2 to 3/2, 1.5. Yeah, 0.5 to 1.5. If our center is at 1, we go left 1/2 and right 1/2. And endpoints including or not including? Non-including, because it's geometric. Good. So time saver. You don't have to test the endpoints. So it is a bit of a booger, but it's probably worth it. And I don't think you'll see anything that sticky and gross on the actual AP exam, that boogery. But once you get through with the algebra, then it's pretty routine. Hopefully, it should be routine. Okay, the last couple things we're going to do here are integrate, differentiate, and then recognize known geometric series or known power series. So if you recall, one of the things we can do is take the derivative or integral of a power series. But what it does, remember, is it keeps the radius of convergence, but possibly changes the endpoints. So you always have to test the endpoints. If they were included before, maybe they are not included now, or vice versa. So find a power series that represents 1 over 1 minus x quantity squared. Now that one's going to be a little bit harder to create by using a known geometric series, because you're not just replacing x with x squared. It's going to be very hard to write it as 1 over 1 minus something. I guess you can kind of expand it and then leave the 1 out and complete the square again. But here's the clue. What is the derivative of 1 over 1 minus x? That'd be a nice multiple choice question, wouldn't it? Boy, if that were just the answer, you would have this is to the negative first. And by the chain rule, you would get negative 1 minus x to the negative second times another negative 1, right? And what's a negative times a negative? Positive, so you end up with 1 over 1 minus x squared. Hey, isn't that the one we're trying to write the geometric series for? Yeah, so if I take the derivative of my geometric series for 1 over 1 minus x, that's one of the things I'm allowed to do. And it'll have the same radius of convergence. I'll just have to check the endpoints again. So let's do that. So if I write my 1 over 1 minus x series out, that's 1 plus x squared plus x cubed plus dot 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 plus x to the n plus dot dot dot. Let's go ahead and take the derivative of both sides with respect to x. And of course, we already know the left side becomes what? 1 over 1 minus x quantity squared. And the right side is going to be the fun side. That's the power rule polynomial side. So I get 1 plus, or 0 plus 1 plus 2x plus 3x squared. Now here's the only bad thing. If I need 4 non-zero terms, I only have 3. Because I started with 4 and one of them went away. So no big deal. The next term up here in the top would be x to the 4th. So what would be the derivative of x to the 4th? 4x cubed. Good. Plus dot 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 plus, and here it is. Real easy. The nth term is going to be n times x to the n minus first power plus dot dot dot. Sweet. Now if we're going to write a series for that, that's going to equal the sum from n equals something to infinity of n times x to the n minus first power. What n would I have to start on to get my first term to be a 1? A 1? Yeah, good, a 1. Which is a little bit different than what we're used to because usually with geometric series we start at 0. But what happened when I took the derivative? I lost the first term. So I've lost the 0th term. So now I start at 1. And that's why it's important to always consider that right there. Okay, so now that I have it in this format, now I need to test the endpoints. I know that the old interval of convergence was negative 1 to 1, but because now I modified it by taking the derivative, I need to test the endpoints again. Okay, so derivative or integrals keep the radius, but possibly change the interval, so test the endpoints. So this is kind of again what we did on Friday. Let's go ahead and test by plugging them in over here. So at x equals negative 1, we get sigma from 1 to infinity of n times negative 1 to the n minus 1. Converge or diverge? That's an alternator, but it's like 1, negative 2, 3, negative 4. That diverges, yeah, by the alternating or by the nth term test. So I can't include that. And let's try at x equals positive 1. I'm going to get n equals 1 to infinity of just n times 1 to any power is just 1. So it's just n. And of course, that also diverges by the nth term test. So the new interval of convergence ended up being the old interval of convergence, just from negative 1 to 1. Now, if this is like a free response, you could probably figure out the radius of convergence without actually going through the step. If you realize the function 1 minus x has a vertical asymptote at 1, that's where the vertical asymptote is, and the center is at 0, how far is it from the center to the vertical asymptote? 1 unit, okay? So it's 4. If you look, or 1 unit, sorry. We have one over here. Yeah, same thing over here. If this one is centered, this one is centered at 0, and it has a vertical asymptote at 1/2, the radius is probably 1/2. Now, of course, we modified the center, and the radius did come out to be 1/2. Last one here. That was derivative. Let's look at number 11. Find a power series that represents the natural log of 1 minus x. Now, some students memorize the natural log, but this one is not just the natural log of x. It's the natural log of 1 minus x. I wouldn't recommend that. And it's centered at 0. Okay, we can't center it at 1 because it doesn't exist. But if you notice the 1 minus x piece right there, that kind of looks like geometric. So here's the hint. What is the antiderivative of 1 over 1 minus x? Well, if you were to do that, you would say that 1 minus x is in the denominator to the first power, right? The derivative of that is negative 1. And you're only off by a negative. So you have a correction of a negative. And when your inside function's in the bottom to the first power, the antiderivative is the natural log of the absolute value of 1 minus x plus c. So if we're trying to write an expression for the natural log of 1 minus x, and I know that the derivative of this, by the way, the absolute values go away. So what can I do? I can actually, term by term, find the antiderivative of my known geometric series, and then do what to make it negative? Just change all the signs. Okay, so let's do that. 1 over 1 minus x is 1 plus x squared plus x cubed plus plus x to the n. And if I integrate both sides, I'm just going to put, I don't want to draw that in front like we do when we solve separable differential equations. I'll just put integrate. I know the antiderivative here is negative natural log of 1 minus x plus c. And we can actually limit ourselves to positive or negative values. And I don't need the plus c over here. So now if I anti-differentiate on this side, again, we're going to need the plus c, so I'll put it first. I get c plus, and then 1 becomes x, 1/2 x squared plus 1/3 x cubed. And one more, 1/4 x to the 4th plus, and we have our nth term, so we can just integrate it, x to the n plus 1 over n plus 1 plus ... And now how are we supposed to figure out, first of all, the value of c? Well, let's do something else first here. Let's get rid of the negative because we're trying to make it look like this, and I have an unwanted negative. So if I multiply both sides by negative 1 now, I get the natural log of 1 minus x equals ShamWow c becomes still a new and improved c minus x minus 1/2 x squared minus 1/3 x cubed and minus 1/4 x to the 4th plus ... plus, I'm just going to put negative x to the n plus 1 over n plus 1. Now this is not quite right. I need to figure out what c is. So how can I figure out what value of c is? Well, here's what we have to do. If it's not given to us, we need to figure it out. Remember that the series, regardless of the radius of convergence, the series and the function it represents always have the exact same value where? At the center. So if this is supposed to represent the natural log of 1 minus x, what is the value at the center when c is 0? Well, you plug it in for x, and you get natural log of 1 minus 0, which is the natural log of 1, which is 0. So I have created my own ordered pair at the point 0, 0. So at 0, 0, I get 0 equals c minus 0 plus 0 minus 0 minus 0. So c equals 0. So the natural log of 1 minus x turns out to be just negative x minus 1/2 x squared minus 1/3 x cubed. And this is why I was writing that extra term. Had c turned out to be some non-zero number, then I would only need to write the constant with these 3 terms, because that would be 4. But in general, if they ask for 4 and you give them 5 terms, that's fine, as long as they're all correct. I wouldn't volunteer it. Negative x to the n plus first over n plus 1, and then plus ... Okay, one last thing here. We need to figure out the radius and interval of convergence. So if you want to write this series now as the sum from n equals something to infinity, of negative x to the n plus 1 all over n plus 1. In order to get my first term of negative x, I need to let n equal what? 0. I start at 0. If you plug in a 0 for n, you get negative x over 1, which is negative x. Let's see if the endpoints work. What would be the old radius? Yeah, it was 1, okay? So if I test out the endpoints, if I plug in a negative 1, will a negative 1 work? You can actually pull this negative here, because this is not like the quantity negative x. This is just like a negative number times x. So much like in an integral, you could pull that negative out front. And let's just think about it. If x is negative 1, what is negative 1 to the n plus 1? That's an alternator, isn't it? So would negative 1 to the n plus 1 over n plus 1 converge or diverge? It would actually converge, right, by the alternating series test? Because without the alternator, 1 over n plus 1 decreases and goes to 0. So at x equals negative 1, the radius is still 1. But we're going to be able to include negative 1 because it makes it converge by the alternating series test. And we would need to show that. We're just short on time. And what about the right endpoint? What about when x equals 1? Well, what's 1 to any power? Just 1. So now if x were 1, I just have 1 over n plus 1, which is no longer an alternating series. It's just 1 over n plus 1, which would what? Diverge by comparison to a p-series, a divergent p-series. The harmonic series, actually. So I cannot include 1. So there's one where when we integrated, things did change. The radius is still 1, and the center is still 0, but the left endpoint became inclusive because now when you plugged it in, you got a convergent series. So this is kind of an interesting one. You'll be told whether to integrate or differentiate, which is nice. You don't have to make that connection on your own because that's kind of hard to tell. But once you realize that when you integrate, you're going to have this unknown value of c. And if they don't give you an initial condition, just realize that you're going to create your own by finding the value of the function, which you will know in advance what function it's representing at the center. Okay? So I'm going to stop right there for today. Tomorrow is Toga Tuesday, and we'll work number 12, which was similar to a 2008 pre-response question. And then we'll finish up with some known geometric series or known power series evaluated at a known value. And then we'll just mosey right into Lagrange error bound after lunch.